Hello, today we want to talk about fast deterministic CUR matrix decomposition. As we all know, in real world we have to deal with enormous matrices. It could be a problem, so that's when we might be a little smarter and decompose and compress our data. For example, we can use singular value decomposition in feature extraction in machine learning and data compression. CUR decomposition is used in model reduction, speed up of computations in numerical analysis and matrix factorization. So what is CUR decomposition? CUR is one of the data compression methods. CUR is divided into three matrices, C, U, and R. C and R are subsets of C columns and R rows of the original data matrix, respectively. U is inverse matrix at the intersection. The other name of this decomposition is rarely used in articles, so we firstly didn't notice what this decomposition is. You can even guess. This decomposition has been a popular method due to its high interpretability. This is because the decompositioned matrices represent the initial matrix, but without excess data. There are several types of CUR decomposition. The main idea is to reduce the problem of CUR decomposition to convex optimization problem. The original deterministic CUR algorithm complexity is NP squared. The central article of this project proposes this complexity in its method. But in the worst case, the complexity can again reach NP squared.
The decomposition search problem is reduced to a convex optimization problem with sparsity-inducing norm. At the bottom of the slide is the coordinate descent procedure is presented, updated with the formula wi 1 minus lambda and so on, where the vector z is actually a pseudo-gradient vector, which is represented by the bottom expression. Next slide. The idea of speeding up the algorithm is that at each iteration we build an optimality condition score for each row of matrix W. Then we construct upper and lower bounds of this score to understand what particular rows in matrix should be zero and which should be marked as significant and preserved in the next iteration. Next slide. The idea behind stochastic CUR, which also used in this work, is to estimate low-rank representation of the original matrix first with SVD, for instance. Then we construct so-called normalized statistical leverage scores, which play a role of weights to sample the columns of interest. And with them, we actually just sample these columns of interest and so on.
To sum up, there are the main differences between the stochastic and deterministic approaches. Stochastic algorithm is much faster, usually 10 iterations with one set of parameters k and epsilon was enough for reasonable plot shape. And it still was faster than one iteration of deterministic approach. On the other hand, the deterministic algorithm always has one unique solution for each lambda choice, has only one parameter, and does not utilize SVD. Here we present analysis for three different matrices. First one is the matrix of a radial basis function. Red and orange lines represent dimensions of the U matrix, and the blue line represents relative Frobenius norm. As you can see, the stochastic algorithm can provide a better approximation, but only when the rank is really low. This is the same data, but error is plotted as a function of our approximation rank. We also provide SVD approximation for comparison. The next example is a low rank matrix constructed as a sum of 10 diodes. One can see that both stochastic and deterministic algorithms converge immediately after the dimension is higher than 10. For deterministic approach, only column selection was performed for the time reduction. This is the same data, but compared with SVD approximation. We conclude that for truly low-rank matrices, CUR works just fine and represents the initial matrix in the meaningful basis. Finally, we investigate the case of a random matrix. Needless to say that the approximation converges only after we reach the minimum dimension of the initial matrix because this matrix is full rank. Again, we show an expected result of comparison with SVD.
So let's discuss CUR versus SVD. A CUR approximation is used in the same way as the low-rank approximation of the singular value decomposition. CUR approximations sacrifice accuracy in comparison to the SVD, but they compare favorably in two key ways, both stemming from the fact that rows and columns are original to the initial matrix, rather than left and right singular vectors. The matrices are more interpretable. The meanings of rows and columns in the decomposed matrix are essentially the same as their meanings in the original matrix. There are methods to calculate it with lower asymptotic time complexity versus the SVD. As for the differences, we could say that CUR is highly interpretable in comparison to the SVD, and C and R in CUR are not unitary. U in CUR decomposition is a pseudo-inverse matrix on the intersection. Next slide, please. So as for the applications of this decomposition, one would be electroencephalography. So spatial filters lack the ability to drive the data, so it will perceive noise in absolutely empty channel as a brain signal. So in some channels, we might get noise and disturbances, which will interfere with the interpretability of results. One of the solutions offered is called spatial selection. In general, spatial selection involves optimization of the quality of the input data set, spatial filtering process for the CUR decomposition approach. So with help of CUR, we can get rid of uncorrelated channels with noise. Next slide.
There is another way to use CUR decomposition. We consider the case of analysis of gene expression data and in kidney and colon tissues. We try to build a low-rank approximation for this dataset and compare its ability to approximate with SVD. The obtained results can be viewed as rather satisfying, especially considering their high interpretability.
So, should we use it? And if so, when? To sum up, practically, deterministic CUR should be used with caution because of its high computational cost. As for the fast version of the algorithm, it does improve the situation, but only for particular conditions. Well, first of all, the target rank should be sufficiently small, or the matrix should be tall. It is fairly complicated to search for appropriate parameters for both stochastic and deterministic CUR. On the next slide, you could see our references, and you're more than welcome to ask any questions. Thank you for your attention.